Hi guys, like I said to you today, that is tomorrow, I'm really sorry I couldn't be there with you today because I've got this meeting on. So I just thought I'd walk through the lesson with you. Now I've actually made up a PowerPoint which hopefully you guys will be able to follow while you're watching this video, or at least making some notes. So in our last lesson, we were looking at plate boundaries. And I think one of the first things that I guess I really want to go through with you again is the cause of plate movement. What actually makes the plates move? And we know that the plates move because of convection currents within the asthenosphere. Okay, convection currents caused by areas of less dense material moving upwards and more dense material moving downwards. So within the Earth's crust, okay, we've actually got those sort of operations, but what's happening though is they're actually causing some plates to move. How are they doing that? Well, they're doing that through a couple of ways. One, through friction between the moving asthenosphere and the lithosphere, but also through gravity as well. So on the first slide I've got for you is just a note saying lithospheric movement is driven by flow within the asthenosphere. Remember, the lithosphere is solid. So the lithosphere, if I'm going to draw it here, is the solid, and then the asthenosphere below that is more fluid, and it's within the asthenosphere that we have the flow that causes our plate movement. What causes this flow maybe to speed up or slow down? Well, that can be the core temperature, or could actually just be the temperature within the convection current. The greater the temperature, then the greater the movement, or the greater the speed of the convection current, and therefore the faster the plate should move. Okay, let's get on to the next one, and that was talking about plate boundaries and boundaries. And we started looking at convergent plate boundaries, and mainly oceanic to oceanic boundaries and convergent boundaries, or mountain building periods. So the first little picture I've got there is a picture of the world, and it's got some images of some earthquakes, and they show shallow, intermediate, and deep. So hopefully what you should see by those, and if I just put my laptop here, hopefully you'll be able to see. If I zoom in, okay, you can see here we've got areas of deep earthquakes to intermediate to shallow. So obviously the shallow earthquakes are caused by the plate immediately starting to be subducted. Then as the plate moves further and further down into the ground, or into the asthenosphere, I should say, the earthquakes occur deeper and deeper. This sort of image will show us the direction of movement. So we can see here that this plate is moving that way. Over in South America, let me get rid of that. We can see the plates are moving this way. All around this area here, the Ring of Fire, you can see the plates actually, the Pacific Ocean, or the Pacific plate, is being subducted underneath each of these respective continental plates. The only places it's not, down in Antarctica, where we've got a passive plate margin, and here along the coast of North America, where we've got a transform boundary. But we'll talk about that a bit later. So, get the zoom going. Cool. So let's get on to our next plate boundary, and that is oceanic to continental plate boundary. This is one of the most complex, and I did draw a picture of this in one of our last classes. We actually have our oceanic crust, and as it's being subducted underneath the continental crust, which I'm going to draw here, continental crust is far thicker, but a lot less dense. I'm going to draw a nice volcano up here. Hope you guys can see that. Okay, features of this type of boundary. Well, firstly, we have to start right at the point of contact, and that is our accretionary wedge. This is a really important part because what's actually happening here is all of the material that sits on top of this crust gets scraped off by the continental crust, and it forms this melange of sedimentary and metamorphic rock. Now, as I mentioned here, over this oceanic crust, we've got a great deal of sediments and water which is being pushed into the crust, and it forms a lot of layers. Sometimes we call these layers pelagic layers. And interestingly enough, in these sort of layers, we can get oil and gas deposits forming, most often because of the organisms that lived in the ocean that have been deposited down there have started to break down, forming those hydrocarbons. But one of the main things that's happening here is we've got a lot of water and it's being pushed into this crust. So our thick basaltic oceanic crust that's being subducted down underground, into the asthenosphere, is chock full of water. Now, as it goes down, it forms a series of earthquakes. I'm going to draw them here. And these are the earthquakes that you can see on the image on the PowerPoint that I've just shown you. We've got shallow, and then we can move down. We have deeper or intermediate, and finally at the bottom we've got much, much deeper earthquakes. Now, you might notice that some earthquakes can actually form around the 300 kilometre mark. Now, we're probably talking way, way, way down the bottom here. Why do we get earthquakes down there? Well, if you think about it, this crust, this oceanic crust, is subducting right down under. And remember here, it's not liquid, it's a solid. So all of this crust is literally being forced down, and it's creating lots of earthquakes. Right deep down, deep down, up to 800 kilometres deep in places. So remember that the mantle and the asthenosphere, it's solid, it just moves a little bit like a liquid, but very slowly, but it's still very much solid. Okay, let's see what happens here, because here is a very interesting point for us. It's a critical point. It's around this sort of point here, and I'm not going to give you a temperature range, but it's upwards of well over 1,000 degrees, where our crust starts to lose all of the water that's inside of it. What's happening? Well, the crust releases a lot of the fluid. So I'm going to write this here. I'm going to write little a, crust, and I'll put oceanic. Releases fluid. This can happen anywhere between 80 and 180 kilometres. Let's draw it like there, 80 to 180. So, when we've got water entering the asthenosphere at this point, it does something to the magma or to the molten rock that's here. It lowers the melting temperature of this rock, and it actually makes the water that enters here makes this solid rock start to melt. It actually makes some of the silica-rich minerals, and it actually creates a basaltic magma, a magma that's made out of stuff like pyroxene and olivine and feldspar. So it's a basaltic magma, maybe a little bit of amphibole in there as well. Okay, so here we've got this magma, and it's not the crust itself, it's just the water that's changing this magma here. What it does is this magma now starts to rise because it's different from everything else around it. This blob of magma that's had lots of water in it is now less dense, than the magma either side of it. So it's going to want to rise up. It wants to rise up, and it will start making its way upward. It makes its way upward in these upside down tear shapes called diapirs. Now, as this magma rises up, it changes itself. I'm going to talk a little bit about how this happens later, but our basaltic magma, our pyroxene, olivine and feldspar, which we're going to call a mafic magma, as it rises up, it changes. It changes into a felsic magma. It changes from one type of mineral to a different type of mineral. Now, you might remember when we were talking about metamorphic rocks, how some minerals are what's called polymorphs. That means they change depending on the conditions around them. Well, the same thing happens here. With the conditions that are very deep within the ground, very hot, we end up with this type of magma. But as the magma cools, the conditions cool and the minerals in it change. Mafic magma is low in silica. Felsic magma is high in silica. What it means is it means these volcanoes are rich in silica. And when we start talking about volcanoes, this becomes very, very important. So let's go back to our plate boundary. We've got volcanoes. We have large sections of continental crust. In some parts, you might find a fore-arc and a back-arc basin, just similar to your to the ocean-to-ocean plate. And if you look on the deep focus earthquakes slide that I've got on the PowerPoint, you'll see that it's demonstrated fore-arc and back-arc basins. It still exists, but it's not underwater. Again, with the next slide, where we look at the focus of earthquakes in Japan, again, I've tried to demonstrate how we can see that we have changing depth of earthquakes. And as you look at it, you can see that we actually, as we move across, if I show you this image here, there we go. If I show you this image here, again, you can see we've got our shallow earthquakes moving to deeper. And hopefully that's that there. Okay, so an example of these sort of locations, Japan is our best one, Indonesia. But by far one of the best examples of these type of boundary is South America. In particularly, the West Coast. And I have a nice slide with a great picture of South America on it, and you can see, you can actually see all of the volcanoes. If I hold this there, you can see all of the volcanoes on the west coast of South America. Okay, next type of boundary is, I think we've talked about collision boundaries. Yes, all right. Next type of boundary is called a transform boundary. A transform boundary is simply defined by movement that is shear movement. So a transform boundary is demonstrated like this. If I was to draw a box, a line down the middle, this plate moves that way, that plate moves that way. We end up with shear movement. The best example of this sort of location is in a place called the San Andreas Fault, and that's in California. Now, if we think about the type of movement that we're going to get here, well, it's actually not going to be volcanic because we don't have any openings within the crust. The crust isn't opening apart. It's not allowing magma to come through. We're not pushing anything together, so we're not making any mountains. all that you'll get is you'll just have shallow earthquakes. Now, that's not to say these earthquakes aren't dangerous. They're very, very dangerous and they can be very destructive, but they're not the type of earthquakes that are going to cause any, I guess, volcanism or anything like that. And I think I've put a couple of slides on transform boundaries. Now, transform boundaries aren't always found along the coast of continents. In fact, they're mostly found in the middle of the ocean. Because the Earth is round, when we have a divergent boundary where plates are moving apart, it will form, I guess, a circle like this. However, nature doesn't work perfectly like this. It won't form a nice arc. But what you'll end up with is I guess, a bit of movement this way. And then you'll end up with a transform fault. And then you'll have a bit of movement this way. This is at a divergent boundary. Then you'll have another transform boundary and then another plate movement. So along the ocean floor, you can actually see divergent plate boundary here and transform plate boundaries alongside it. And it just allows the Earth to still be a circle and spread open. But I think I'm going to have to demonstrate that one in class. I've put a PowerPoint note on transform plate boundaries and hopefully you should be able to see that. I'm not going to say too much more about transform boundaries at the moment. All that happens really is the two offset. It's shear movement, side to side movement like that. And man, that's about it. Best example, San Andreas Fault, California, shallow earthquakes. That's what you need to know though. Okay, let's go to our final plate boundary, and that is a divergent. So divergent boundary. Divergent plate boundaries are fascinating. It's simply where the Earth opens up. Two plates move away from each other. It can occur in the ocean, or it can occur on the land. With each, we get different features. Within an oceanic, we get what's called a mid-ocean, a ridge. With continent, in the middle of a continent, we get something called rifting. Deep within the ocean, you'll end up seeing along the oceanic crust just a point where two plates meet. As they're being spread apart, magma pushes its way through to the surface, causing this mountain range in the middle of the ocean. And then magma pushes its way to the surface, solidifies, and forms a rock. Within the continental, though, it's a lot different. There's a lot more work going on. As the plates are being moved apart, we end up with features that look a little bit like this. These are called horsts and grabens. And they're caused as the plates are pulled apart. Just like you'd pull apart a snake, if you have a lolly snake, if you pull it apart, you notice it gets thinner and thinner and thinner. Well, the same thing happens to the Earth. As you pull it apart, the crust simply spreads and spreads and spreads until it snaps and breaks apart. Now this is happening in the middle of Africa, right in our East African Rift Valley, and it's happening right down here. I'll put this PowerPoint, you should be able to see that page. Gives us a bunch of really unique features, but it also gives us some amazing volcanoes, which I'll talk about when we look at our volcanism a bit later on. Another example of, so I'm going to write down here the African Rift Valley, and for our mid-ocean ridge, I'm going to put our mid-Atlantic ridge. Now the Atlantic Ocean is brilliant because it runs right through the middle of a small country called Iceland. If you ever get to go to Iceland, it's a pretty cool place, lots of waterfalls. And the Mid-Atlantic Ridge runs right through the middle of Iceland, literally ripping Iceland apart. There's not much more to say about that really at the moment, but I've put a little slide on for you. It's just a good example of I guess, continental rifting, but in an oceanic context. Okay, so next part, questions. I've got some questions that I'd like you to look at. I want you to have a go at answering. Let's do that now. Question number 1. How fast do plates move? Easy. Question number 2. Why do some plates move faster than others? 3. Why does oceanic crust subduct and not continental? 4. Does oceanic crust melt when it is subducted at a convergent, and I'm going to go oceanic to continental boundary? 5. Can California expect volcanoes, volcanic activity this year, and why? Question number 6. Why is Iceland growing? That's an easy question. Last question. Ooh. Question 7. So, I want earthquake depth. I want you to tell me which places are going to have deep, shallow, or both earthquakes. Here we go. I want for each of these. Number 1, let's go with Mount Fuji. B, Mont Serrat. It's in the Caribbean. C, Lake Victoria. D, don't want to say obvious places. Let's go with let's go Los Angeles. Oh God, I can't even spell today. E. And lastly, earthquake depth at Bali. And F, earthquake depth in a place called Quito. And I'm going to leave that for you to find out. Okay, I hope you can see those questions. How fast do plates move? Why do some plates move faster than others? Why does oceanic crust subduct and not continental? Does oceanic crust melt when it's subducted at a convergent boundary? Can California expect volcanic activity this year? If so, why? Why is Iceland growing? And tell me, at each of these locations, Mount Fuji, Montserrat, Lake Victoria, Los Angeles, Bali, and Quito, does it have deep earthquakes, shallow earthquakes, or both? Good luck. I'll see you tomorrow.